Well, hello. Got no joiners today, so I'll be talking alone to you. That's all right. Today we are looking at 110, and this is our last unit, Unit 7. And Unit 7 is completely different from any of the other units we've covered. So we have left acoustics that we did before the midterm, and we've left now psychoacoustics, which we did after the midterm. It's time to turn our attention here to something that's more applicable to the field and more practical, and you're going to be using some of the acoustics that you learned in order to understand non-electronic acoustic modifications. Non-electronic, meaning no wires connected, no battery. We're not talking current and circuits and no. Just the shape of things. Okay? The shape of the hearing aid. The shape of the hearing aid. Okay, stuff regarding the mass and the stiffness stuff about the hearing aid. Nothing electronic, okay? But these things do change the frequency response. In other words, they change what's happening with the hearing aid. They change the gain that the hearing aid produces. So that's why we're covering them. So when we start, I'll share screen here, and let's go to our notes, and let's see what we've got. So if I pull up the notes here, you will see this, non-electronic acoustic modifications. Generally, a lost art. I'll bring it a tad closer so you can see it a little bit closer, okay? Most hearing aids today are digital, which allows for an amazing amount of frequency shaping. But non-electronic acoustic modifications are techniques used when fitting quite inflexible analog hearing aids. Now stop here for a second because there are 3 non-electronic acoustic modifications. Write these down and you'll see them below in your notes as well. Actually, I can scroll down and you'll see it. So let's look at it here. There's 3 of them. One's called venting. Okay? The other one's called damping or filtering. And the third one's called horns. And notice how each of these covers different frequency regions. And these are ways of modifying what the hearing aid is doing at these particular frequency regions. Okay? But let's just go back up to the top before we get into them. Let's just look at this preamble here, this introduction here. Non-electronic acoustics modifications are techniques that were used more in the past and not as much now. But hang on a second, this one here is still used a lot. Venting, big time. Damping or filtering, not so much. Horns, not so much anymore. But venting, yup, you betcha, very much. So that's why it's important to make sure we understand that. They help shape the frequency response of a hearing aid. Any good HIS should have a handle on them. Besides, implementing these principles is cheap. Okay, recall this from acoustics and from anatomy. The resonance of your outer ear canal, or EAM, it's like a cylinder closed at one end. So it's a quarter wave resonator. So it's going to resonate when it's a quarter the length of the sound wave, or when a sound wave is 4 times its length. And there you go. The external auditory meatus is 2.5 centimeters long, an inch. 4 times 2.5 is 10 centimeters. 10 centimeters equals 0.1 meter. So what is the wavelength, or what is the frequency then? Frequency equals speed of sound divided by wavelength. Wavelength is speed of sound divided by frequency. Just like 5 is equal to 10 over 2, 2 is equal to 10 over 5. Okay, that's all we're doing here. So remember the formula. Do not forget it. Okay, frequency equals wavelength over, or speed of sound over wavelength. All right, so here you go. Speed of sound divided by the wavelength, 0.1 meter. 340 meters per second divided by 0.1 meter, 10 centimeters, equals 3,400 hertz. So the resonating frequency of your ear canal would be 3,400 hertz. But The external ear canal is flesh and bone and cartilage, so its resonance is spread out. Remember that? It's made of flesh and bone, and its compliant tympanic membrane also transmits and reflects energy. Whatever the point is, the exact frequency is fudged a bit. And so the resonance of the outer ear canal and outer ear concha and all that stuff extends from about 1,500 to 4,000 hertz. And its peak resonance is about 2,700 hertz in the average adult, slightly higher in a kid because of smaller canal. And here's the point: hearing aids plug up the canal, and they destroy this natural key of listening, because you're plugging up the canal, and now it's a cylinder closed at both ends. So the hearing aid thus has to restore this lost resonance and also make up for the hearing loss. Also, 2,000 to 4,000 hertz are very important for understanding speech. And some ear molds, and now I'll stop sharing for a second here, some ear molds plug things totally up. Okay, and thus you're affecting stuff as to what's going on. I'll share screen one more time here. 2,000 to 4,000 hertz are very important for understanding speech. Some ear molds do not let enough highs get into the ear. For high power hearing aids, beware of narrow tubing. What do I mean by that? For high power hearing aids, I'll show you here's a high power hearing aid. The tubing is this. If this tubing gets really narrow and skinny due to it's old, it's shrunk with the heat, and it's now narrower, when you narrow a tubing, you're preventing highs to get through. When you widen tubing, highs can get through. And we'll learn about that more as we carry on in this particular unit. We're going to spend 2 weeks on this lovely unit. So this is just interesting stuff. So here we go. Let's look at a PowerPoint presentation now. Here's a PowerPoint presentation on the same thing. And this is a little bit of what you're going to be doing, taking ear mold impressions. Let's look at this guy here. Okay, there's your ear. And when you take ear mold impressions, you're going to stick a sponge into the ear canal, almost all the way up to the tympanic membrane. And then you're going to be mixing material together to squeeze into the person's ear to make the shape of the ear mold. And you're going to use the bottom here, it's called an ear light. And you're going to use that to push the sponge into the ear so you can see what's going on. You're mixing the material together and you're sticking it in a syringe. And you're going to squeeze this stuff and put it into the person's ear canal, thus filling the entire ear canal with goop. It's like a silicone that hardens. You have to be very careful to make sure you brace when you are doing this. You need to brace when you're putting an otoscope in someone's ear to look. Okay? You need to brace when you are sticking a thing in, when you're pushing the sponge into the person's ear canal with the ear light. Always brace your hand. And what do I mean by that? You can't just go, okay? You need to be having a finger against the side of the head so everything is moving as a unit, okay? So that you're careful not to be pushing something in someone's ear. You need to always brace. And there's various techniques for bracing, but we'll get to that at another time. You'll learn it later. Here we go. So there's the syringe, and these are impressions made in order to make the ear mold. And again, ear molds, I'm going to stop sharing. Ear molds are not always like this. This is an ear mold for a behind-the-ear hearing aid, a BTE hearing aid, behind-the-ear hearing aid. And you can see it's got a hook on the top, and I can take the tubing right off the hook, okay? And I can put the tubing back on. The tubing holds the ear mold, and this tubing is exactly 2 millimeters in diameter. It's 2 millimeters in diameter, okay? And it's called number 13 tubing. Number 13. Don't ask me why. That's what it's called. And we'll talk more about that next week as well, but I'm just giving you a heads up. Many of today's hearing aids, this is a high power hearing aid with an ear mold, okay? More popular hearing aids today are smaller. And look at how thin the tube is compared to this tube, okay? And this is called a thin tube behind the ear hearing aid. This thing here that sticks down the bottom, that's just meant to go inside the concha bowl, to fit up in here. It helps hold this thing in place. In other words, this. And this is called a dome. I'll turn it so you can look at it. It's a dome, okay? And it's kind of a stock dome. It's not made for any particular person, okay? It's just meant to fit into an ear canal. And there's different sizes of domes. Here's another dome. I just took it off a hearing aid, okay? It's just a little rubber tip. So you can have either an ear mold or a dome. And a dome is more popular. And domes are more applicable to people with mild to moderate hearing loss. Hearing aids like this, severe hearing loss, okay? Anyway, we don't want to get ahead of ourselves, but we're just looking, okay? So back to our PowerPoints. There you go. So you've taken an ear mold impression, and this is for that high power BTE with the number 13 tubing with the ear mold, okay? Here's a good one. You can see the sponge still stuck at the end. You can see the long canal, and you can see the entire concha bowl is filled. That's a good ear mold impression because the manufacturer can take this and can cut whatever you don't need. They can cut that off. It's always better to provide too much material than too little. Here's too little. Insufficient canal length. Okay? That's no good. Okay? Your ear canal, remember from anatomy, has 2 bends in it. Your ear mold impression should cover both bends. This bend and this bend. Remember, your ear canal is shaped like a dog leg, okay? It's crooked. It's got 2 bends in it. And that's why when you're looking in someone's ear canal with an otoscope, as you learned in 120, you have to pull the hearing aid or the ear up and back. You pull the pinna up and back, and I'm going to show you closer. You pull the pinna up and back to straighten out the ear canal so that when you look in, you can see the eardrum. Otherwise, when you look in, you won't even see the eardrum. You have to pull the ear up and back to straighten out that dog leg. Very important. Ear mold impressions need to include both bends. So there you go. Undersized ear canal due to inadequate block results in feedback in the hearing aid. The hearing aid's going to whistle. Underfilled helix will not lock in ear. Okay, what do I mean by that? In the ear mold itself, there's the helix part. Okay, it has to all fit inside the person's ear. So you got the canal portion and the helix portion. So this is why ear mold impressions are made out of a material like plexiglass, and it's called lucite, L-U-C-I-T-E, lucite, okay? Some ear mold impressions are made out of silicone. Here's one made out of silicone. It's rubbery. See, I can bend it. That's silicone. Silicone ear molds are often for more profound hearing losses. This one's called a full shell ear mold. Can you see how and whereas this one here is called a skeleton ear mold. This is lucite skeleton, and this is silicone full shell. Full shell means you're really trying to prevent any excess sound from bouncing back off the drum, leaking out and getting picked up by the mic. Then it gets amplified, bounces off the eardrum, leaks out, gets picked up by the mic. You get that vicious circle called feedback. Just like you talking into a mic in a room, and when you go too close to the speaker, all of a sudden you get ee. That's because sound from the speaker, as well as your voice is talking into the mic, but now sound from the speaker itself is entering the mic. And then that gets amplified and comes out of the speaker and then enters the mic, and you get that vicious circle. That's feedback. That happens in a room when you're talking in a mic and you go too close to the speaker. Well, it's going to happen in a hearing aid if you're producing a lot of sound and it leaks out and gets picked up by the mic. You're going to get feedback. So high power BTEs for severe to profound hearing losses often have silicone full shell ear molds. And when you walk around and you see someone with a hearing aid like this, with a silicone mold, you can rest assured that guy's got a severe to profound hearing loss. You're going to have to be facing the person, and he's going to be reading your lips at the same time. He's got total hair cell damage. He's got both inner and outer hair cell damage. He's got a major hearing loss. Someone wearing a hearing aid like this probably has less of a hearing loss, more like a severe or moderately severe. And then someone wearing a hearing aid with a dome, okay, has a mild to moderate loss. And remember, this cord here, this wire that sticks down here can irritate you because I'm always showing it to you, but remember that just sits in the concha bowl, okay, and helps hold the dome in place in your ear canal. Good. All right. Just show and tell. This is much more of a show and tell type of Zoom session here. But now let's share and go back to our PowerPoint slide here, and we'll move on. There's the ear mold close up showing you the two bends, bend and bend, okay? The two, and here's the helix and the concha portion. And the manufacturer is going to cut this all off, cut off any of the excess, and is going to build the ear mold from the impression that you sent. So to give an old saying, you never get a second chance to take that first impression. Make it right, okay? And you'll learn this in your practical. Now, when you're looking, here's a bunch of ear molds laying side by side, okay? On the left is a full shell, silicone. Don't worry about this one. Here's the middle one. That's a lucite skeleton. So this one here and this one here are the two ear molds that I was showing you earlier. Okay, half skeleton, skeleton, and then they get some other really weird ones. Don't worry about them. Leave them alone. The ones I want you to know are full shell and skeleton. Today in class, this is at another college program, George Brown College in Toronto, Ontario, Canada. And I used to teach there years ago. There's a fella who's teaching there now, and he showed me an ear mold impression that he took on a student. To read what it says, "Hi Ted, today in class a student got an ear mold impression stuck on a barbell piercing in the person's ear. It took 15 minutes of very careful cutting to free the impression." So I guess the student had some, what do you call it, a pierced ear of some type, and had some piece of metal that got surrounded on the ear mold impression. And as it hardened, because the ear mold impression is made of silicone, and it hardens after 5 minutes, and that's when you take it out of the ear. But you can see the sponge at the end, okay? Here's the ear canal portion. And it probably has the two bends I can't see, but here's where they really had to tear and carefully cut away so that they could take the ear mold impression out of the person's ear. Yikes. Okay, now this is getting back to what we were talking about in our notes regarding the ear canal as a quarter wave resonator. Okay, so here's an ear canal on the top. Sound entering the ear canal. Now, it's going to have that resonance. Because it's a quarter wave resonator, it's going to resonate with sound waves 4 times the length. And it's going to have that resonance sort of spread out because the ear canal is made out of flesh and bone, not out of glass or steel. And so instead of having a particular frequency resonance at 3,400 hertz, its resonance will be spread out between about 1,500 hertz to 4,000 hertz, with a peak at about 2,700 hertz. And what's the decibel gift of it? What's the vertical axis in terms of height? This peak here will probably be about 20 dB. Okay? So you're looking, here's how we perceive it. It's just normal. We don't perceive anything weird about this. To us, just the way we hear is normal. Now, when you take the bottom panel, and you're going to see that, hey, you're sticking a hearing aid now inside the guy's ear canal, and it may have a frequency response like this, but guess what? Because you've killed off the resonance of this guy's ear, okay, your frequency response is going to look like this. So the hearing aid has to really make up for the lost resonance and add gain for the hearing loss. And that's what the first paragraph of what we were talking about here in our notes, that's what this is all describing. Okay? And then as you move down in our notes, you can see ear mold types and materials. Lucite skeleton, by far the most common if you are wearing a high power BTE. Softer materials like silicone are good for kids preventing injury during play, but they also tend to reduce feedback due to a tighter fit. And think about that. I think plexiglass or lucite, sure, it's going to stick in your ear canal, but if it's silicone, it's more rubbery, right? And that's going to adhere to your skin even tighter. And that's why silicone is often used with full shell ear molds for severe to profound hearing loss, because hearing aids for severe to profound hearing loss are going to be giving buku gain, okay? So the more they're pounding out, the more you have to try and prevent feedback. Okay, and then as the hearing loss is not quite as bad, the hearing aid doesn't have to be quite as strong. Now you're dealing with a moderately severe to severe loss. You can get away with the lucite skeleton mold. Less occlusion, less plugging up. And you always want to use less and less. Okay, so then it's less visible, everything else. So now let's look at our three things, the way we can modify frequency responses in a hearing aid. Non-electronically. Venting controls the lows up to 1,000 hertz. Damping or filtering controls the mids from 1,000 to about 3,000. Horns tend to control the highs, 3,000 and above. Horns and filters were relied upon big time in yesterday's analog hearing aids. Not used much in today's digital hearing aids, because today's digital hearing aids are very, very flexible, and you can really flip and move things around a lot with all the different channels in a digital hearing aid. You can literally sculpt and shape the frequency response quite exquisitely. So you don't need to rely on these two modifications as much. But the one you do look at, though, there is always a tension between vents and horns. Now look at the venting here, this one controlling the lows, and this one controlling the highs. There's a tension between those because vents affect low frequencies and horns affect highs. And horns, well, let me just talk about a horn here. What do we mean by a horn? Good grief. Let me grab a piece of paper. And roll it up like a horn. There we go. If I talk backward into the horn, I'm cutting off my highs. If I talk this way into the horn, I'm increasing my highs. So, what do we say about high frequencies? They're short. Low frequencies, long. What else did we say in acoustics about low and high frequencies? Lows bend, highs bounce. So if your hearing aid is providing a lot of amplification, and most people have trouble hearing treble, right? Most sensory neural loss affects the high frequencies. Bass hearing is pretty good in elderly people. It's usually treble. Okay, so your hearing aid is naturally, you're amplifying high frequency sounds. And high frequency waves are going to bounce off the eardrum and leak out and get picked up by the mic, causing feedback. And vents are holes. Look at this ear mold. I'm going to take it off the hearing aid. See how it has two tunnels through it? The top tunnel is for the tube. So the sound is going through the tube, through the top tunnel, and into the guy's ear canal. But notice there's a bottom tunnel. And that bottom tunnel is a vent. Now it's hard to show, so I'm going to point at it very closely. Where can I show that? The vent is right here. See, I'm sticking my pencil into it. That's the vent. And that carries on right through here and goes to the end. So again, note two holes. I know it's hard to see, but there you go. There's two tunnels. One's for the 13 tubing, and the other one is a vent. And what do vents do? The bottom hole. It allows low frequencies to escape. But if the vent, and you want the lows to escape, you know why? Because of the occlusion effect. And when you plug your ear, go ahead now, plug your ear and hum. Where do you sound loudest? In the ear that you plugged. So that's why with a hearing aid, you're plugging up the ear. So the guy's going to hear his own voice really loud. That's the occlusion effect. The occlusion effect is a low frequency phenomenon. So you use a vent to allow the lows to escape. What is the occlusion effect again? Let's repeat it. The lay definition. This is straight out of 120 anatomy, okay? The lay definition, the common definition of the occlusion effect. Your voice gets louder in the ear that you plugged. The professional definition. Write this down. There's 5 pieces to it. And you've had this before, so that it isn't new. This is out of anatomy. Low frequency, bone-conducted sounds resonate the mass of your skull, which in turn vibrates the cartilaginous portion of your ear canal. Plugging the ear prevents that added resonance from escaping. 5 things. Low frequency bone-conducted sounds resonate the mass of your skull, which in turn resonates the cartilaginous portion. Plugging your ear prevents that from escaping. Now go ahead and plug your ear and say the letter S. I'm repeatedly plugging on. Little bit of difference. Now hum. Bigger difference. Okay? The occlusion effect is a low frequency phenomenon, kicking in more when you hum as opposed to when you s. Okay? So venting allows the lows to escape. You know why? Because with venting, you are increasing the acoustic air mass in your ear canal. You're allowing the air in your ear canal to communicate with the air in the room. And therefore, you're increasing the acoustic mass of air trapped behind the ear, the hearing aid. And mass resonates with low frequencies. So the low frequencies, like following Hansel and Gretel out of the woods who are leaving their breadcrumbs, the low frequencies are going to follow that. They're going to go where the mass is. So a vent increases the acoustic mass of air trapped behind your eardrum. Therefore, lows will escape out, and the occlusion effect then gets reduced. Okay? That's your number 1 acoustic modification, venting. And now back to the tension again between horns and vents. Horns increase the highs. Highs are high frequency waves are small and they bounce. So guess what? If your vent is too big, the highs are going to leak out and get picked up. You want the vent just to let the lows out. You don't want the vent to let the highs out. So there's always a bit of a tension. And so you kind of, as a clinician, you want to find the biggest vent you can, but at the same time, you want to prevent feedback. So you're trying to fight the occlusion effect with the vents, but you want to increase the high frequency amplification too, because the person has trouble hearing treble, can't hear sh. So you're trying to do two things, but like an artist, you're going to have to balance things. That's what I mean by the tension. Okay? Very, very, very important. Now we'll share screen and look at our notes. And what do we have regarding venting? So let's read it. What does it say? Venting is a short, wide hole in the ear mold done to reduce low-frequency amplification. It creates more acoustic mass, thus allows lows to leak out. Larger vents allow more lows to escape. In other words, they reduce the low-frequency occlusion effect even more. Venting reduces the occlusion effect, especially, now put a star by this, especially for those with good low-frequency hearing. So for whom are vents made? People who have good low-frequency hearing, because they are the ones who are going to hear the occlusion effect the most. If you got good, poor hearing in the lows, you won't hear the occlusion effect very much. In fact, the occlusion effect is a benefit to you. You want the occlusion effect, okay? But if you have excellent low-frequency hearing, you're going to need a wider vent because you're going to really hear the occlusion effect otherwise. Now, there is such a thing called a select event right here. Select event helps you as a clinician. It helps you work around that tension. And select events are really weird. They look like, let's see if I can show you. Oh yeah, select event. There you go. Here's a picture of a select event. Here's a mold on the left. Number 13 tubing coming in. Here's the vent hole. So manufacturers will drill that vent hole in, and this, you've sent in the impression. The ear mold will be made for you. The tubing will be stuck in it. It's all good, okay? You need to size it properly to fit it onto the BTE, and you'll learn how to do that. But basically, this little black thing is a select event, and it looks like this guy right here. And you can see how these are all measured in millimeters. The smallest one is just a pinhole. And as they get bigger and bigger and bigger and bigger, the largest vent hole you're going to see is 4 millimeters. The smallest you're going to see is 1 millimeter. If a vent hole is only 1 millimeter, let me show you some select events here, just right on the screen. Here's a little tree, this little rubber thing here. And it's got a whole bunch of vents on it. So I'm going to see, and it's got all these little tiny vents. Now look at the holes. And it's kind of hard to see, but let's see if I can get a piece of paper here to hold behind. You see how the holes are bigger on the left, and they're getting smaller and smaller and smaller as you go to the right. Kind of hard to see, but it's called SAV, select event. And it allows you to take one of these off of here and stick it into the hole in the ear mold, much as you saw in this particular picture. So if we go to share screen here, much as you saw here. Okay, so you can plug it in and you can work around that tension where you can say, okay, what's the biggest vent hole that I'm allowed without creating too much excessive feedback at the same time? And feedback will happen because you're trying to amplify the highs, because most people have trouble hearing treble. You want the vents to reduce the occlusion effect, but at the same time, you don't want the vent to be too large so that you keep getting feedback. Okay, therein is the tension. Now, if I go all the way back home here, woo. Okay, and we'll move through our slides just to make sure we're all in order here. This is a speech spectrum, as you've learned in acoustics. Most energy is in the vowels. That's where you're going to get the occlusion effect. But you want to amplify the high-frequency consonants. A, they are softer, and B, most people have high-frequency hearing loss. I will repeat. Unvoiced consonants, letters S, F, TH, K, they have less energy, look at my cursor, and the person has high frequency hearing loss. That's why you're going to have to amplify the highs by a lot. You don't need to amplify the vowels very much. A, they're louder, and B, the person doesn't have much hearing loss in the lungs. Okay, so you're fighting the occlusion effect by means of vents, and you're trying to amplify the heck out of the treble with the hearing aid. Again, here's speech sounds on an audiogram. Here it's showing you in the speech spectrum in dB/SPL. Now you're looking at speech sounds on an audiogram, where 0 dB/HL, as you've learned in acoustics, is really minimal audible pressure, the curve. And you're looking at the sounds of speech shown, and now the decibels here, of course, are getting greater as you're moving down, whereas here the decibels are getting greater as you're moving up. So when you're looking at it on the audiogram, all voiced sounds that use the larynx are louder and lower. Unvoiced consonants are softer and higher. Again, showing you the very same thing as in this picture, only in dB/HL. Outer ear canal resonance, there it is again for you, just like out of 120 anatomy, the physiology of the outer ear, why the length of the canal is the way it is, all of this stuff, the quarter wave resonator, as a result, you get this kind of resonance, and it's got all the values on there that you need to know. 20 decibels is given, especially between 1500 and 4000 hertz, with a peak at 2700 hertz, right there for you. And here it's showing you now hearing loss on an audiogram, the inability to hear these high frequency sounds, and hence the gift of the outer ear canal resonance. But still, that gift of the outer ear canal resonance isn't enough to increase the audibility of these consonants, because the guy has high frequency hearing loss. Okay, so while this is great for normal hearing, it increases the audibility of high frequency consonants. When you've got sensory neural loss, of course, it's not enough. So here's the effect of your 3 non-electronic acoustic modifications. Venting is the big one. It affects mostly the lows. It addresses the occlusion effect. Damping or filtering isn't used as much today, neither are horns. But this is a picture showing you the general frequency regions affected by each of these 3 non-electronic acoustic modifications. Now, on the left, you're looking at venting. In the middle, you're looking at filters or dampers. On the right, you're looking at a horn. Look what happened to the tubing. Look at how it turned from 2 millimeters to 3. You've got the horn. Okay, and what happened when I showed you on with my paper and I made a horn? Horns increase the highs. So, there's select event for you. Now, let's go to our notes here so we don't get ahead of ourselves. Select event. There you go. You should know the general sizes. Wow, a bird just flew into the window. He didn't get injured though. He flew away. Anyway, select events. The largest ones are generally 4 millimeters. The smallest ones are basically 1 millimeter. Okay, what's a millimeter? Please remember, a centimeter is the width of your fingernail. A millimeter is 1/10 of a centimeter. Parallel versus diagonal vents. For high power BTEs, parallel is better. Well, why is that? Here's parallel on the top. The hole for the ear, for the tubing, number 13 tubing is there on the top. There's the vent hole. It's parallel to the top one. Those are the best. Here's a diagonal vent. It's used when someone's ear canal is too small to accommodate a parallel venting system. So this here is not as good, because you're making the vent intersect with the tube, the number 13 tubing. And this kind of situation is going to allow highs really to escape even more than they should. So try never to use diagonal venting. The only time you're going to be using venting like that is shown on this slide, of course, is for the high power hearing aids. Because the other kind of vents are in the domes. So let me show you the dome of a hearing aid. Once again, the dome. Now, if I take the hearing aid away and I hold a piece of paper behind this again, Look at that dome. Look at all the holes in it. You see all the holes in that dome? That's a real holy dome. Okay? That's got lots of vents. The venting there is huge. It's kind of hard to see. And if I show you here, another dome that I'm holding up here, look at all the holes that thing's got. Here, against my shirt, you can really see that, okay? Maybe that's the way I should have held this too. See all the holes? See, these are they're heavily vented domes. So you can tell right away this kind of a dome was meant, whoops, for someone with good hearing in the low frequencies. Because not all domes are like that. Some domes on hearing aids, okay, some domes on these hearing aids have less holes in them. They're less holy, okay? They're more covered. And you might use those kind of domes for someone with a more flat hearing loss. Someone whose hearing in the low frequencies is maybe 30 or 40 dB instead of normal. Okay? So real holy domes are meant for people who have normal hearing in the low frequencies, like 0 to 25 dB. When you get beyond 25, you're in mild hearing loss category. So now you're going to have, you may not want to use such a holy dome, okay? You might choose out of your packet that comes from the manufacturer to stick a dome on the end of this BTE tubing that has fewer holes in it. Because you want a little bit more occlusion effect. You don't need to reduce the occlusion effect as much. The guy doesn't have excellent hearing in the lows. So your domes can get more and more solid, more and more plugging. And then once you've worked if the guy's got, let's say, a flat hearing loss of about 60 dB, then you're probably going to be considering more like the actual ear mold. And I can't find mine now. It's all spread out on the desk here. An ear mold, okay? And then you're probably going to be going toward a behind the ear hearing aid. That's more like this, and you're going to be coupling the mold onto the hearing aid itself. Okay, and then you've graduated from this kind of hearing aid to this kind of hearing aid. Okay, so I'm just going through general styles of hearing aids and non-electronic acoustic modifications. The biggest one to consider is the venting. Back to sharing screen so we don't go ahead of ourselves. Let's look at our notes now. Okay. A pressure vent. Put a star by that one. A pressure vent is a very small vent. A pressure vent is a vent with 1 millimeter diameter or less. A pressure vent is just meant to equalize air pressure. It's a comfort issue. It's too small to address the occlusion effect. It's too small to really let very much lows go out, okay, to escape out. So it's mainly meant so that when you take the ear mold out, you're not sucking out the eardrum along with the ear mold, if you know what I mean. Okay, it's a comfort issue. Note on PowerPoint slides where vents are seen on BTEs and ITEs. Okay, let's do that. Let's look at that. Oh, by the way, this is showing you reduction of occlusion effect. DBSPL, closed ear mold, solid line, and now you're getting 1 millimeter vent. It allows a little bit of the lows out. 2 millimeter vent allows more lows out. 3 and 4, so the bigger the vent hole, the more the lows can escape. Influence of vent diameter on the occlusion effect. Here's another picture showing you in terms of gain in simple dB, whereas this one's showing you output in dBSPL. Once again, the bigger the vent size, the more the lows are allowed to escape out. Now, we are kind of getting ahead of ourselves. I don't want to get into filters, but let's just show where vents can be seen on ITEs and BTEs. So let's just see if I can show you. I haven't got the PowerPoint to show you, so I think what I'll do is just show you in person, like stop sharing. Here. Here's an ITE. a great big old ugly ITE. Looks like a piece of bubble gum stuck in your ear. I mean, this is not pretty. I mean, if I put this puppy in my ear, it doesn't even fit well, but I mean, okay, people hardly wear things like this anymore. Actually, that's in the wrong ear. Let's just put this guy here. There you go. So look at that. There's an ITE, in the ear hearing aid, full shell. Not very common anymore. You don't see this very often. But if you do, okay, it will have a volume control. It will have a battery door. Stick your battery in, close it. It'll have a vent. Here's the vent. And if I turn it around, you're going to see two holes. The white one is for the sound to come out. The bottom one is the vent. Okay? Behind the ear hearing aid. So if I stick this guy in my ear, I'm going to just wear these now. I'll stick it in my ear. This is a left ear mold. And I'll wear the hearing aid. Okay, so now I got the hearing aid in my ear. Okay, here's the mold. The hearing aid is stuck like a beige banana behind my ear. Not pretty, but good for severe hearing loss. Now why don't I take this hearing aid here and try it in my ear. So I'll put it in, set it behind my ear, and then just take that little tubing. Okay, now, there you go. Okay, a lot less visible. Look at how thin the tube is. Okay, it's less than 1 millimeter in diameter. What did we say the diameter was of this kind of number 13 tubing? 2 millimeters in diameter. 2 millimeters in diameter. Okay, that's hard to see, but there you go. 2 millimeters. This, less than 1. Okay, probably 0.8, 0.9 millimeter. This is today's hearing aids. This is what most people are wearing. They're often called receiver in canal. This one's a thin tubing hearing aid, a thin tube hearing aid, but its close cousin looks a lot like it, but instead of having just a thin tube for the sound to go through, there's actually a wire going through. And so the speaker of the hearing aid is actually in the ear canal, surrounded by the dome. So you can take this hearing aid here and stick a dome on it. There you go. Okay, but the receiver, the speaker of the hearing aid, is right where my finger's pointing. Whereas in this hearing aid here, the speaker is actually inside the hearing aid, and the sound is going through the tube and into my ear. Okay, this is called a thin tube hearing aid. This one's called receiver in canal hearing aid. They look very similar. There's not much difference between the look of them. In fact, a man on a flying horse would be hard pressed to notice the difference, okay? They look similar. But the point to remember, thin tube, sound goes through the tube. The speaker is in the hearing aid. And in hearing aids, the speaker is called the receiver. Okay? Hearing aids have a mic, which changes sound into electricity. The electricity is amplified, and then the electricity is changed back into sound by the speaker. A speaker is a backward mic. A mic's a backward speaker. Okay? And in hearing aids, the speaker is called a receiver. Thin tube hearing aids and behind the ear hearing aids, no matter what kind of hearing aid it is, I can put the mold on this guy here. All the time on all these hearing aids, the speaker is inside the hearing aid, and sound goes through the tubing into the mold. It's the same with thin tube, only this one's thinner. Receiver in canal is usually the most expensive one. That means, and I'll show you now in a picture. Let's look at our PowerPoint slides to make sure we have this down, because we're nearing the end of our session here, and we'll finish this section next week. Okay, we will. I'm just going to show you a couple of things here. Okay, here. This is a thin tube BTE. That is exactly the one I showed you. Okay, the very same one I showed you. If we carry on down the page, here's thin tube, open fit, behind the ear hearing aid. There it is again. the tubing, the speaker is in here, sound goes through the tube and into the ear. Here's a picture of it. It's sitting in the ear. There's the dome. There's that little thing that rests against the concha bowl. Okay, that little wire is this over here. Thin tube effect. Thin tubes tend to cut the highs. They tend to cut the highs. So the hearing aid has to make up for that. Remember we said thin tubes cut the highs, horns increase the highs. So thin tubes have this war to deal with. But when you're going to receiver in canal, that's called a RIC, R-I-C, RIC, receiver in canal BTE. They look a lot like the thin tube, except here a wire goes through the tube, linking the amplifier to the speaker or receiver, which is inside the dome. Okay, so now the speaker's closer to the ear, whereas in thin tube, the speaker is in the hearing aid, behind the ear, sending sound through here. The thin tube, I should say the RIC, the sound is coming from here. So receiver in canals tend to cost a little bit more than thin tube. Okay, the most common hearing aids today are receiver in canal hearing aids. This is the most popular hearing aid in the world. This is the one, I'll bet you 75% of people wearing hearing aids today are wearing RIC BTEs. Well, this has been fun. Let's just kind of now go to our notes and see where we are. Now, next week, we'll look kind of at filters, dampers, which are tiny screens. We'll talk more about that next week. We'll talk about horns a little bit. Next week, we'll talk about the tubing that's used in BTEs a little bit more, and we'll kind of summarize this particular unit and wrap it up. So today we've gone through most of the material in this unit, non-electronic acoustic modifications in hearing aids. Next week, we'll finish this unit with a discussion more on filters and horns, but today has been big time on venting. Be sure you know the occlusion effect. Be sure you know what vents do and why they do it. Be sure you know the millimeters of the vents. Okay? It's today's most commonly used non-electronic acoustic modification. All right, with that, live long and prosper. I will stop share, or I will stop recording here, and it's now, yeah, we're about 10, 12, it's about 12:25, 12:23, something like that, so we're good. We've done our little Zoom session for today. I'll stop recording, and we'll see you next week for what I believe is going to be our last session. I think we're done next week as far as material goes in 110 acoustics. All right, so the purpose of today was to kind of take what the acoustics we've learned and to apply it more directly to the hearing aids that you're going to be fitting. It's been a slice. I'll stop recording now.